Yeah, so Milan, please go ahead.
Okay, then thanks a lot for the kind introduction and for having me. Pleasure to talk about workflows. I hope my title doesn't disencourage because it's titled with the simulation, but I will also mention a lot about how this fit into experimental and potentially industrial work during the talk, or at least most of the stuff we can also transfer. So, quick introduction. I founded a small company, startup, you can say. We are mostly operating as a technology partner for deep tech industry. So from research universities to other startups mostly that we consult and build bespoke platforms for them, mostly in the cloud, but also sometimes on premise. And yeah, the topics are quite wide ranging from basic, so digital infrastructure, server management to full stack applications and particular workflows. So on the one hand, on the top, you can see our research platform as from the last years. It's now in use for like 4 years more or less and used by a couple of university groups. But we have also industrial projects, for example, at the bottom right from Cisco Sensors, they develop very nice magnetic sensors for monitoring bridges, infrastructure, and others. And here we also developed workflows for the sensor manufacturing, for example, but also fully modular IoT pipelines that are working in the cloud. So, what will we look at today? It's really the research perspective, as I have worked mostly in this regard, but most of the stuff will apply to other topics as well. So, I will start with a short vision of the research automation of tomorrow or how it could unfold without claiming too much here. And of course, where the current problems are, what is so difficult and realizing this vision of fully autonomous laboratories and so on. And then I brought to you some kind of new architecture that I've been working on quite intensively, how how we can build a real nice orchestration system that can handle all these challenges. And we look at this a little bit more in detail and in practice with a short examples, an outlook, and a final summary. So let's start with the challenges, or better to say, the vision that slowly comes to be in our minds and how research of tomorrow should look like. So we have a lot of topics converging on each other. For example, we have like the idea that we interconnect labs to another to have some central storage, some central overview of what's going on, and also, of course, increased automation in our laboratories. So from robotic arms that might insert samples to fully autonomous measurements and so on. We have, of course, the rise of AI and its capabilities from early optimization algorithms that could already be employed quite successfully over the last couple of decades to some newer chances we have with large language models and especially multimodal models that can even look at data and make some kind of interpretation of data. But of course, this needs new tools, new guardrails, and new ways to utilize. And then we, of course, have the computational side of things. So simulations that accompany all of this simulation campaigns spanning multiple GPUs, multiple servers. We want to work in data centers. More and more compute is available to us, and more infrastructure is around that allows us to access this more easily. And of course, what we can see, I guess, as a natural cause of a globalized world, we see in more and more federated research. So also the research supply chains get more complex. We have suppliers of raw materials. We have different consortia, each group specializing in some kind of work. Often we have experimentalists and theoreticians working together. We have the industry that provides use cases and also is actively researching as well. So firstly, let's maybe look at what drives innovation, and we can make a very crude assumption here that innovation just equals the amount of experiments we do and our ability to learn from them. So how good are we from learning from past experience and these are our levers if we want to improve research. And on the one hand, we can say, okay, we want better automation uh, to gain more samples, to gain more data. And on the other hand, we want smarter planning systems, maybe better memory of the past, better organized data that drives our learning efficiency. So maybe making better predictions of where to look next is of the essence and can really scale our insight generation rate, if you will. So in the end, we can more or less summarize um, the challenges for the scaled innovation, or however you want to call it, lies in workflow systems that allows and enables better automation and of course better planning systems that allow us to really exploit our data better. And this shouldn't mean that it is just more robots, more AI, but most of the stuff is really at the time of being, I would say, an infrastructure problem, and humans will remain in the loop for the foreseeable future, I would say. So the automation claim is there, but take it with a grain of salt. I mean, it's still a lot of human work in between. But we can even make this human work more efficient, I would say, by giving it a proper architecture and better interconnection with the automated systems. So by that, I want to give you a rough model in how I think about a workflow system or the system design in the background for better automation, for better research. And I come here with very crude abstractions, but that should show where the pathway is going for more automated research. Of course, this is a very crude abstraction of the real world, but it still allows us to give it a nice context. So starting off, we can summarize each experiment or simulation or even industrial manufacturing steps, if you will, as this kind of very crude mathematical statement of just we have a function, so some experiment, some simulation, some analysis, some human tasks, our F. We have some input parameters that might be the sample, some simulation setup, or some other kind of parameters that feed into this task. And then we have, of course, some output, some measurement output, some measurement results, some simulation data that comes out of it, or maybe even a manufactured part. And to get a workflow, of course, we want to be able to combine these individual steps with each other. And then we expect we have a starting parameter set, and it goes through our workflow. And in the end, we get a nice result from the composition of individual steps. So each individual step must feed the next one. And now if we go one step further and think about how we can, make automated research in some sense, or even semi-automated research, something informal could also describe this, our a formalism that rates the outcome. So the quality of our result, the quality of our insight, or if you already go into a little bit the perspective of the optimization algorithms, you can call it a reward function. So that takes the initial parameter, our final result, and grades it for an outcome, whatever that grading might be. That will very much dependent on the use case. And then to drive the full loop, so to have a continuous research loop, we might need to make a prediction. So where would we want to look next? And here, I call it planner. Our strategy comes in, and it basically takes all our past observations, all our past rewards, and based on the past results, our learning, so to speak, we want to make the next prediction. So the next parameter set that we want to try out. And the planner can be anything. In some cases, it might be a human researcher that tells some other system or some other researchers what he wants to investigate next, but it can also be an LLM, a large language model, or an optimizer that, based on a given strategy, decides which parameter set should be picked next. So maybe the task or the job of a researcher might evolve into just modeling these four components. It likely isn't everything to the story, but it is a perspective I want to give you today. That we just need to design and define and model these four things. So the planning strategy on how we learn and derive the next parameter set from our past outcomes, the reward function, which is very crucial to choose, and the workflows itself, including our parameter definition or parameter modeling. But of course, to really work in this direction, we need a new set of tools because in the end, this is a very big orchestration challenge and a lot of steps are in between that we need to overcome. And this is a very hard effort by many that need a lot of people and different industry and different tools come together, of course, to fully realize. So in the end, I would say that this is about challenges in the realm of data logistics, of integration of all these different moving systems, and of course of orchestration of the whole continuous loop that we want to achieve. So if we now want to look a little bit into where things are today and how to or what challenges we really face. Of course, we have this abstraction. We say, okay, one experiment is one workflow. But of course, there are a lot of individual hurdles and steps to overcome from sample handling, from informal practices that are not properly documented. It's just someone knows how to do, but he didn't document it. So the lab operator that done the experiments for the past 5 years, for example, you have a lot of hardware to integrate and to command and control different vendors, different APIs, and it's not always easy to control them. And other thing are infrastructural challenges, like how do we even reach this laboratory? So often we have the isolated networking environments. Not always you can just ping the laboratory computer and say, hey, give me all your data. Most often there are some IT challenges to overcome, and reproducibility is not always a given factor. So sometimes you just have environment drift, hidden parameters that you don't record properly. And yeah, with that, you also might have some other data that is not recorded properly, and this allows you to draw the right conclusions. If we look at the other side of the equation, we have simulations that we also want to, of course, put into this nice abstraction here. But also here we have a lot of things that we need to take care about. It's might look easier, but yeah, there are still a lot of challenges to have this really as a reliable part in our workflows. So on the one hand, we have more often than not now the aim to parallelize across multiple servers, across multiple runs. One workflow might involve several hundreds of simulations, for example, if you do a parametric sweep, for example. And yeah, we have timing issues, we have network partitioning, all sorts of problems that can occur. We need to stage our software environments at best in a way that is reproducible and is not so much dependent on the host and the versions that are installed on the host, because then you end up in a mess that you need to administer and spend a lot of time getting on the same page. So containers are, for example, some way to do it. And of course, we need to have a proper management of our access and secrets to data centers, and also need to check if our view of our simulations is actually the truth, because you can have crashing PCs, crashing code, and all sorts of reasons why your simulations might not behave. as you wish. And this, of course, also requires proper monitoring and proper extraction of our results. So, all in all, we have unfortunately still a world where failure is everywhere and all around us. So, unfortunately, we can't just say we build a system and we have quite some assumptions and we have some code, some singular code, and everything is fine. No, everything will crash at some point. Every failure that can happen will happen, especially the longer your continuous research loop runs. So it's not so much anymore about algorithms and planning and design of experiments. I mean, those are not gone, those are still big challenges, but it's really about how can I design a system that remains resilient and robust in the case of failure. Because everything, yeah, will fail at some point. And this shouldn't mean that you lose the state of all your data, maybe a simulation that run for a few days. You don't want to lose this because then it will be very hard and you need to be very lucky so that your week-long running research pipeline concludes successfully. And so this is kind of the core challenge that I want to solve with my architecture and with my platform that I'm currently working on. That is kind of a combination of different approaches that allows us to really face these different failure scenarios and handle them gracefully. So now we come a little bit into a formal chapter where I want to introduce a few concepts from computer science before I want to show you how we can apply that for research workflows. So overall, if we look at the landscape of our research infrastructure, we have, of course, a lot of things that are already there. We have data centers, we have workstations, we have maybe file servers that are there. And more we also see people using cloud systems, cloud storage, for example, or some institutional hardware, some industrial company infrastructure that already exists. And the idea is now that you don't, let's say, uh, force people to throw everything away and here's the new architecture, here's the new software. You need to install it on every PC of yours and be done with it. Such a solution won't work in practice. So, and of course, it wouldn't also be feasible because you can't just rewrite all the software of the past decades that have evolved into this very robust states. For example, Slurm orchestrator for data centers for high performance computing, or some experimental setup. You won't rewrite those. The idea is more of deep integration and deep coordination so that we can have a central control plane that knows how to speak to all these different federated systems and coordinate the workflows across them. So we need to work in very heterogeneous IT environments. It's a bit funny if you write such code. It feels more like you are writing code for a botnet than for some research infrastructure because you need to instruct every one of those components correctly to speak with each other, to handle the insertion of like your input parameters and the extraction of the results again. But in my view, it's the only path to really make use of what exists and combine this into a smart and intelligent infrastructure layer or orchestration that can span all of these systems. And once you have the central control plane, then the door really opens up for you because then you can orchestrate these workflows spanning this, and you can then be smart about what you schedule. So which experiment should run, which simulation should run, and how we derive insights from this data. And this isn't a benefit that only affects optimizers or make the use of AI agents feasible, but it often also improves the researcher, the human researcher itself, because it forces to have proper data orchestration, proper data archiving, like fair data handling becomes of the essence because every system needs to understand each other. And so this is where I see my part of work is just this kind of central control plane that knows how to combine all these different systems. It's not about giving optimization strategies or something like that, because there are really a lot of them already out there. They are really good and high quality, and all of them are open source. So we have a lot of ingredients ready. But I think now is the time to find the right architecture for these frameworks that span and make them able to use all of these different systems. And of course, I just present one approach here. There are multiple other ways to do it. So, as I said, we need to be able to run in very dynamic, in very failure, in environments where failures occur all the time. That's just a fact of reality. No one can say to a hard disk it shouldn't fail. Unfortunately, it's not possible. And you will also have like maybe power outages. You will have problems with your networking. And so this was one basis to model. And the other basis is, of course, we want to have deep control over our workflows and deep provenance. So we need to really have some ability to see where things are, where are we standing, where are things breaking, which system hasn't contributed and has maybe has a problem. Because of course you need to be able to be good in debugging if you want to have any chance to win. So the first topic I want to introduce here is called event sourcing. It's basically a very nice idea that we don't want to just represent state, so whatever that state might be here. It's the classic example of a bank account that you hear, and it's a technique that almost, I would say, all financial institutions use to have consistency in the bank accounts of their customers. Is the core idea is just that you don't just store the value, the account balance, but you store all the different transactions that led to this final value. Because here you have a system that allows you to verify if the balance makes sense. Every little cent is accounted for because you can always look in the past, look through the ledger, through the transaction log, and see if it makes sense, or if there was a rounding error because some of the software updated and you didn't know, or something like that. And this is a quite a nice idea to build systems that are very consistent or can have a verifiable consistency, so you can always travel back, make sure that everything still makes sense, they are auditable, and if you have a crash, like for example your database fails, you can just travel back in time, look through the transactions, and recover state from the transactions. And by this, we also gain the ability to time travel, basically. I can just go back in time, and to every given transaction, I can see or recover the balance at this particular point in time. So these are quite nice attributes, and I think it's now already hinting a bit where we are going with this. And another cool thing we can do here is also we can make this verifiability even gain more trust by applying a technique that is called hash chaining. So basically, we have the first event, we apply a hashing algorithm to that, then we take a new event and the old hash outcome and apply the same hashing function again. And we can do this in a chain. And so by that, it allows us to really verify the integrity of all past events, of all past transactions. So it's not easily possible for a bank employee, for example, to just change one transaction and suddenly he's a rich guy. No, we can see, this transaction was tampered with, and all the hashes afterwards don't match anymore. And so we can have really a trustworthy system by constructing it this way. But this alone doesn't allow us to represent the very complex workflows that we are facing when doing research. Another quite nice technique to represent state, which is fairly well studied now in computer science since a couple of decades, is called Petri nets. So this is coming from control theory. It's basically a way to model state and the transitions between states. So like a state machine, and we have a formal concept now for this. So every place represents a possible state. Then we have transitions between those, and we have tokens that represent our data, our actual where we are, basically. So to give you a concrete example, we might have here tokens that represent our input parameters. Then we have a transition that might represent a simulation. And then we get some output parameters, some observations, tokens of a different data shape. Just to give you a small example. And on this, we can then build very complex networks, complex graphs that represent our workflows in the end. So we can, for example, very nicely realize loops, which is also kind of a way where it differs from standard approaches in workflow systems that are using these directed acyclic graphs that essentially really disallows you to build loops. That's not every workflow system follows a duck, but very often they do. But of course, if you think about this continuous research cycle that we want to achieve with the planning and reward and chaining of this, we need loops in the end. And this is also quite a nice property of the system that we are able to do that. And we can compose that, we can make concurrency in our system very visible by these fan out transitions, for example, that we just replicate tokens, and each token might represent a simulation. And then we can just look at our net, look at our game board, if you will, and see, we have 100 simulations currently running. A few have transitioned to the next state, and others are still stuck there. So we really have a nice way of observing the state of a highly parallelized and highly asynchronous system and process, which is really science in itself. And of course, we can also do things like decisions routing. So we can have like guards which transition is able to fire and which are not, based on some given condition, based on some token data, which allows us, for example, to um, decide if the simulation has converged or not. And now the fun part starts where we combine these two approaches. So the event sourcing, the event log, looking at all the different transactions from the past and building our state from that, and our Petri nets that allows us to model the workflows itself. So on the one hand, if we combine this, so every event is basically a transition or represents a transition and a token movement, then we can see how we can build a very good system for tracking the data lineage or the provenance of our data, because we can time travel to all the different states in our nets, for example, suddenly, and really see which transformations our final result has undergone through the different points in time, and from which data sources is read, and so on. So it's not a thing that you have to construct afterwards, but it's just really some emergent property that just arises if you model your workflows this way. Another nice thing is that we continuing on this train of thought, we can easily see how we can automatically also discover processes by just looking at tokens that are basically seed tokens or start tokens. And then this is a new process, and every token that comes afterwards as a transformation of that can link back to the start token. And so we have a nice way to build these causality chains. So what results came from what transformations. and say, okay, this is one coherent process. So it's not something that we have to define, but we can just trace how our results flow through the net and say, and combine them. But I will show that in more detail later. But our main objective here was actually just building a resilient system. I think this is the most important property from all of this, that we are able to just replay our past events, our past transitions, and then recreate the state of very complex workflows. So if our control plane should crash in some case or some other problem arise, we can just reboot, look through the event log. Of course, you should have that persisted, um, and then recreate our current state in our measurement campaign, in our simulation campaign, and continue from there. And that's really, for me, was the most important property. So just to give you to visualize this a bit more, these points, here we can see, for example, how this combination unfolds. So we have some initial net state, then we have the transitions that fire, we have one branch that our token takes, our workflow takes, and our event log records all of these transitions. So we are able to backtrace where this token came from, which branches it took through our net topology. And by that, we can also you can look at this like breadcrumbs basically on a trail. We can also reconstruct more enriched views of this process by looking at special tokens, for example. We can leave on this workflow that, for example, leaves some log lines, some metrics, some data hints that then makes us able to create very nice live visualizations and live monitoring systems built on top of this formalism. And here again, the short animation, how this recovering mechanism works. So again, we have some crash maybe, then we can just look at the past logs, recreate our state from there, and then resume from there. Another very important thing is that we can model failures very transparently. So we add, for example, routes that decide if an error, a problem that arises through in a simulation or experiment is a permanent error or a retriable error. And then we just tell the system, hey, maybe schedule another simulation with the same parameters. The last one has failed, and do that for a certain amount of time until we are sure that the simulation really is broken and we should do something about it. So from this kind of very formal work, I want to now continue on to show you a bit of the work in progress state. So again, we've built a past system that works very reliable for these simulation workflows and is used extensively. But now over the last year, we redeveloped it from past learnings. And here I want to show you a little bit of a work in progress state, but it also illustrates a lot of the nice properties already, which we can, and how this might evolve into practice. So these Petri nets might be very, very complex if you model each failure route yourself and something that you can't demand from a researcher to do. Because this really takes a lot of knowledge and lot of experience where systems break and how you handle each failure. And the idea is that we go back to a very human-friendly layer that represents really our business logic in some sense. So what we are actually about to do. And here, for example, is an example workflow just for some data extraction of an invoice, for example. And we have these nice nodes, and this alone isn't a Petrinet. That's a nice workflow representation. So how do we come from here, from this user-friendly editor, to this very resilient system that has all these nice properties? Our approach here is that we have a compiler that takes these steps and then creates basically based on some given formula subgraphs that are verified and work and represent the thing the user wants to express. And then we arrive at these very complex networks that are very robust and very nice, have these different properties that I introduced earlier. But of course, you wouldn't author them by hand. I wouldn't say that this scales any further than it's unfeasible for humans to build. So we have this compiler that can then really make sure that all the different error routes and all the different situations are taken into account. And here you can see kind of the debugging view. It's all, like I said, very early state. But you can already see here at the bottom, we can move through the different events. You see the event log here, and they each represent a different state in our network that then represents the overall state of our workflow in some sense. And of course, authoring by hand is kind of something that goes out of fashion quickly, even with a nice editor. So I guess the real future lies into machine interfaces, APIs, command line interfaces, and of course also the integration to version control systems like Git. And this is all taken into account. The idea is then probably in the future more like, hey, you tell the AI what kind of workflow you want to have. The AI then writes the code, the necessary topology based on these steps, and then the compiler uses the AI output and builds this real workflow that hopefully expresses what you want to do. In the end, you can have this nice graphical representation that allows you to give feedback to the AI and iterate with an AI agent together on your particular workflow. And of course, behind this, we also create a version system that allows us to roll back and really backtrack how our code and how our workflow has evolved over time so that we don't lose this provenance chain in the end. Another extension of this formalism, I would call it, that is very essential and you find in almost all very modern AI platforms or AI factories, you might also sometimes see them called, is a kind of central data catalog. So what we do whenever we see a file being created in some of our workflows, we have a mechanism to extract metadata from it. So we just build a little library, but there are also, I guess, a lot of good open source libraries for that already, that then looks at that file, extracts metadata based on the file type. And then the magic is that we basically also say, hey, this data will be stored in this data storage, wherever that might be. And we register it in the central control plane and inform our system, hey, we have a new simulation result based on a given schema, data schema, and this simulation result is on this file server. And so we have centralization of our data without really having them physically necessarily centralized. So we could have multiple file servers in action, and that's also a good thing to do because you might want to have disaster resiliency. So something should be stored offsite, your really critical data. Something shouldn't move into cold storage if it's like an archive that you don't access regularly. Maybe the work of the past decade isn't as valuable anymore, but you don't want to throw it out the window anyhow. So, and you shouldn't probably. So you move that into more cost-efficient storage options that are, however, not as easily and readily available as some more normal hard disk-based storages. So magnetic tape, for example, is often used for that still because it has quite nice properties for this. Anyhow, this allows you to federate storage and also it allows us to build like decoupled systems where we basically register a new result and another workflow might be triggered that listens to data of this kind and then retrains a model, for example, or triggers some other evaluation of this new result. So we have a way of registering data and a way to subscribe to new data, which really makes your system scale because you have very nice ways to basically decouple workflows. So instead of one monster program that spends like hundreds, thousands of lines of code, you can have a lot of small workflows, a lot of small microservices, you could almost say, that work independently on each other and might be very nice to compose and still be maintainable over a longer period of time. And another nice thing that you can bolt on top of this, like I already presented a little bit earlier, these breadcrumb trails that we can leave inside our networks, some tokens that represent, for example, log lines, tokens that represent metrics like our progress state, or some metadata that's how our whole process, in which phase it is, how it should be called, and so on. We can just then look through the events for these special kind of markers and reconstruct different views of our running process. So the process might run on very different environments in a lab, in a high performance computing cluster. Some of it might be just forms for a human, but here we can allow, we are able to aggregate logs from all of these different systems and then have a combined view of the global state, which is very hard to do actually without proper tools. And very essential, of course, if you have for example, an optimization loop, you need to know, will I converge at some point, or does this whole campaign doesn't make sense anymore because it basically doesn't improve. We are stuck in a local minima. All of these things can happen, and then it can mean, do I still continue for several days of computation and pay maybe a lot of money for it, or do I stop here and be done with it and try the next set of parameters? Another thing we experimentally achieved is kind of an active learning scheme. It was like a base test if our architecture really holds true to these promises. And here we realized, unfortunately not in a very nice workflow level, but really on a PetriNet authoring level, an active learning scheme where we designed a system for Bayesian optimization. So that works basically like we have some observations, some data points. In this case, we did some simulations, and based on these past observations, we built a surrogate model that basically tries to interpolate the physics, the dynamics of the system in a crude way. And it also gives us a score of uncertainty where we are for a given set of parameters. So near known data points, we have low uncertainty, and the farther away we are and the unknown, basically, in parameters we have not tried yet, the higher the uncertainty gets. And then based on this surrogate, we can derive strategies where to look next. So we can, for example, balance between, okay, I want to see something new or try something new. So this kind of exploration, or we know, here's maybe a good neighborhood where we can find a real minimum. That would be the exploitation. And there are very nice toolboxes to balance these kind of things, because we can then just sample our surrogate and have very fast evaluation instead of doing a real simulation. Then we can just look at our map basically and ask this acquisition function, hey, where might be a next good candidate to evaluate? And the evaluation is, of course, a costly thing. Maybe an experiment with sample fabrication, maybe a simulation. This technique can be applied on basically anything as long as you are able to model this correctly. And yeah, and here we did some micromagnetic simulations without going too much into detail here. We can here see at the top a given magnetization configuration, here some skyrmions. Then we have two parameters that we allow to vary, and over time our system converges. Now here you see basically the view of the surrogate. So we have some kind of measure for the uncertainty, and then we have here our acquisition function that tells us where the next point might lie. That gives us a good expected improvement of our reward function, basically. So, slowly coming to an end, giving you some caveats, of course, this is very early days, and I think it still remains to be seen how far this architecture can scale. But I'm at the moment pretty optimistic about it, and I have to say I'm working on this since 6 years maybe now. So I'm quite gotten excited now after all these other different prototypes. I think this can still achieve a lot in the future. But yeah, we have to see. Reality has to tell us in the end. And of course, it also introduces a lot of new formalisms, kind of new concepts that you have to learn. And I guess the best approach to make this really usable is to kind of hide it away behind nice interfaces and good tooling. And of course, yeah, the integration layer is still young, but we can already handle quite a few things like Slurm, high performance clusters, normal cloud services, and other execution layers like human task forms, human in the loop processes we can handle. I think we can also handle laboratories already quite well, but of course, there's still a lot of integration that would be necessary. Quick note on the business model and the things behind it. So the idea is to really make this open source, or partially it's open source, so everything is readily available and you can use it however you want. And part of it is behind an open core license, so the source code is available, but it excludes competing services like offering the cloud service that is basically doing the same thing with our code, something that we want to avoid. The idea is that we sell services based on top of this infrastructure. So a managed cloud service, for example, that makes the operation more cost efficient than managed by us, for example, and also maybe yeah, sell consultancy and other project work. Um, then with that, I conclude. And the moment we are, of course, always looking for cool projects and case study partners. So, for example, for autonomous laboratories, we are very interested in, but also for inverse design or optimization use cases. So, whenever you have an idea that might fit this or can really challenge the system, I would be very happy to hear it. Maybe we can then talk afterwards. So with that, I conclude and thank a lot for the invitation and your attention, and a pleasure to be here. Thank you.
Thank you, Milan, for such an extensive but still profound kind of sharing. I like a lot the concept, in particular, this Perry nets. I thought about how to formulate the workflows and so on previously, but I like this idea very much. Good. Guys, do you have questions or comments? Feel free to unmute yourself and ask directly.
Everything clear?
Yes, or like business models will be further developed. Good. No time to ask a question. I have a few actually. I think then talking about workflows, I think then if I think of the agentic systems, I think then there's a natural kind of continuation, right? So then like after building up such a workflow, then it's easy to use the large language model to drive or to develop such agentic system and then do this quasi automatically. So are you thinking of converting the workflows you are now working on now to such agentic systems?
Yeah, great point. I guess there are two answers to this. So one answer would be the agent in the workflow itself. So you have the LLM via an API embedded that makes some basically predictions or some data extraction from unstructured data. So it looks at a plot and maybe does a trend analysis or some more sophisticated, yeah, derivation of insight from some raw data.
Hmm.
But on the other hand, you of course also have the other side of the equation where the agent is sitting outside and is designing and iterating on these workflows.
Hmm.
So I think both will be uh, part of the future here.
Yeah, so then we could then think of a multi-agent system with also kind of hierarchical structure. So then like then to basically do such workflows after knowing how, of course, to run everything quasi-automatically.
Yeah,
I
yeah,
see.
exactly. Yeah. So we want to apply this in healthcare.
Uh-huh.
This will be very exciting for the next month. That because on the one hand you have this very nice capabilities
Mm-hmm.
of agents, but on the other hand you have to put a lot of guardrails and also like the provenance is so nice here because you want to be able to detect whether the agent just hallucinates
Mm-hmm.
or whether his output is derived from some real prior data point from the.
Mm-hmm. Mm-hmm.
Here we can hopefully really track that quite nice.
I see. Yeah, I think if you have a real physical workflow in mind, so this could probably teach the agent to cooperate in such a, particular pattern to avoid hallucination, right?
Yeah, yeah, potentially, yeah. Or
Hmm.
you have another agent then that again listens to the output of a prior agent and the data sources it has as available, for example, and compares is it hallucination or is it well founded? Does the
Hmm.
source make sense? All of these guardrail systems you're basically able to build on top then.
Sure. Good. So then I'm also happy to see that you are considering such a data catalog. And so I think then this is a hidden kind of a layer, so to say. Without this properly tackled, I think then probably it's very challenging to get such workflows in production. But then in this regard, so what is your take on a proper way of structuring data. I think then for companies, probably they know, but then for a particular niche field, you can also try to fake the standard. But then if I'm thinking of getting if not the real world, like a lab completely digitized, then you need to really, in particular, get the similar labs, like also incorporated in the future, I have a lab here in Germany, another one in the States, somewhere in China, there's another one. So they are all producing or they are all working, following the same workflow, let's see, but then they are generating data in their own kind of a style. So then have you thought about how then this could be like kind of unified?
Mhm. So the approach I'm currently following here is basically you have a particular set of metadata that you can always assume is there. So
Mhm.
file size, file name, where it's stored, and who might have created it. And then you have another part of it that is basically more or less free form because you can't account for all data types.
Mhm. Mhm.
You might have some extraction that is shared, some extraction mechanism that is shared between collaborators, and maybe you end up at the same metadata, maybe not. So the idea is that you don't store it in a fixed format. Like,
Mhm.
of course, you want to have it, but you need to allow flexibility. And modern databases allow that. So on the one hand, you query the structured part, but also the unstructured part as JSON or like
I see.
visual data
Mhm.
um, supporting this. And then I guess it's not that big of an issue as long as you have access to the raw file again,
Mhm.
because then you can just build systems that, like, as long as you can subscribe and query this catalog, you can say, hey, give me all the files from this collaborator that are similar.
Mhm.
And then I enrich them with my mechanism, with my extraction code, and enrich the metadata so that it's standardized to my view of the data.
Mhm.
So as long as you have these tools, it's not a big problem, I would guess,
I see.
assuming the data is somewhere to be found.
Uh-huh. Good. Yeah, yeah. I mean, yeah, I get the a flavor of what you mean. But in this regard, so thinking of kind of such a parallel, let's not call it competition, but a production at a different places. In order to avoid such kind of repeated efforts, while keeping the the results properly copyrighted. So then in this regard, um, what is your kind of vision, or let me be more specific. Do you think we can like develop a similar system like blockchain? So then we can say, okay, I have already achieved such kind of production using such a workflow under such conditions. I get this registered in the system so the others, they do not have to work on it. So, what is your opinion on this?
Mhm.
Or what are the challenges to get this implemented?
So on the one hand, yeah, I think that's like hard to tell in general because on the one hand you have like the public space, like the public repositories, Zenodo, and these fair catalogs.
Yeah.
And I think from my point of view, where I see our work realistically fit in is more or less at some point we upload or we give the publish button and
Mm-hmm.
then we give all the metadata and everything we can find in our system, publish it there, and then delegate trust to this system.
Mm-hmm.
As long as we stay in our mechanisms, we can, of course, do this kind of blockchain approach because we have this event log of all the past transformations and the history of our data. We have these hash chains, so we can really verify uh, quite trustworthy, I would say, who has created it and that the integrity is still there and so on.
Mm-hmm.
So it depends on where these ecosystems develop. I think, yeah, I think this is kind of a system that I, for the reasonable future, see at a consortia level. So maybe shared between a few partners, but not necessarily public, but who knows?
Mm-hmm. Yeah. So then I'm happy to see that your framework is ready to be tested for autonomous, kind of experiments. In this regard, if I'm thinking of like such kind of vibe coding and so on, so there, basically what is your expected outcome. But then for autonomous experimentation, then there it's very hard to really establish, like a specific goal, seeing that this is something I'm expecting from this, because for research and so on, it can be like kind of open-ended. So then in this regard, so then how could we then try to justify seeing that, now with such a kind of agentic system or workflow, we reached our goal. So then, if you want to do such kind of set up such a criteria, what would you do?
Yeah, I think that's really the difficult part that is often skipped when someone presents optimization or inverse design things.
Yeah.
The formulation of the reward function is
Mm-hmm.
insanely complex and takes a lot of intuition.
Mm-hmm.
And it, yeah, basically can drive everything in some very unforeseen consequences. So,
Yeah.
I think that's a job in its own and a science in its own.
Mm-hmm.
For example, you can like also create for novelty or for anomalies, and there are ways to do it, but it's always very use case dependent.
Mm-hmm.
I think the idea is more that you have the harness so that you can experiment more quickly with different reward functions, with different hyperparameters of your study.
Mm-hmm. I
But
see.
I'm also like still collecting experience for this.
Mm-hmm. Yeah, but I mean, if we could then try to, through such kind of construction of workflow, get then the whole production procedure digitized as an optimization problem in the parameter space, I think this is probably easier for us to really tackle this problem, right?
Yeah.
Yes. Good. Yeah, I think I'm done with the questions I have from the scientific point of view. I have a few questions regarding your suggestions or your advices of launching some startups. So what is your like let's see one sentence summary till now, on the market,
On the market,
the
okay.
most important one.
Yeah. Well, I guess if you start, you're not selling a finished product, you are selling yourself. I think
Hmm.
that's very important to realize.
Yeah.
And on the other hand, you shouldn't wait too much with that. I mean, I faced a lot of issues in the beginning because I come directly from university and
Hmm.
from the science perspective, and there you want to have really trust in your system and a very nice result, and you're a bit shy and like have very high expectations of yourself. But the most successful founders are often those that start with very crude prototypes and
Hmm.
just very early on have contacts to users. Luckily, I had some in the university as my experimentation groups
Hmm. Hmm.
to gain feedback early on. But yeah, this is like the main problem that many face in research, that they wait too long to get out. And then, of course, coming from research, you always also have this problem that you most often have some nice technology and you're searching for problems where you can apply that.
Yeah,
Uh, That's like very hard to do. So founding from science, I think, is the biggest challenge of them all.
I see. So then we should not be too like see we should be more brief to try out to
Yeah.
enter the market and see what is really needed there and then try to adjust the strategies rather than just wait for whatever.
Yeah,
Yeah,
exactly. Yeah.
I see.
Yeah.
Interesting. Good. Probably I will try as well on my own, but who knows? Like at this point, you see my hesitation. Good.
Mm.
Uh, I will then stop recording now. So, guys.